Okay, today we are going to talk about diffusion MRI. First, what is diffusion? Diffusion is the random motion of small particles, maybe water molecule. Actually, it's Brownian motion. Then why do we need to measure diffusion? Diffusivity is intrinsic characteristic of tissue. For example, fluid, they can diffuse freely, so their diffusivity is high. And solid tissue, in contrast, they cannot diffuse so freely, so their diffusivity is low. And the diffusivity of tissue can be changed by pathology. Most lesions, they may have restricted diffusivity, so we call them diffusion restricted lesion. In different type of diffusion restricted lesion, they have different diffusion level, so we can characterize tumors or lesions by their diffusion level. For example, cystic lesion, they have higher diffusion or diffusivity level than solid lesions. And in particularly, tumor, within the tumor necrosis is more liquid, so it has higher diffusivity than the surrounding tissues. Diffusion can have clinical MRI, clinical applications like detection and characterization of lesions and evaluation or prediction of tumor treatment response, but it's more than that. Diffusion can be measured using MRI technique. We call them diffusion-weighted imaging. Basically, it's a specially designed pulse sequence that is used to measure the diffusivity of tissues. Before we go into the technical detail, we want to keep some most important clinical conclusion in mind, and later on we'll gradually explain why they look like that. The diffusion restricting lesions, they look very bright in DWI images, so it's easily to detect them in DWI. We just find the bright spot. They are diffusion restricting lesions. However, some other tissues that has long T2, they may also look bright in DWI images. So it's false alarm. We call this case T2 shine-through effect. In order to differentiate the false alarm T2 shine-through effect from the lesion that we want to detect, we can generate ADC map, which means apparent diffusion coefficient map. In the DWI images, it contains both the diffusion weighting and the T2 weighting. So these two cases, they both look bright, but we only want to detect this. So we want to eliminate the T2 shine-through or identify the T2 shine-through. Then we generate this ADC map. ADC map basically is a post-processed image from the DWI image. DWI image, we acquire it use special sequence, and ADC is just post-processed from DWI. In the ADC map, diffusion restricted lesion, they will appear dark. So if we just focus on the lesion, then it looks bright in DWI, and ADC, it looks dark. So we want to detect using DWI. But here in the ADC map, the DWI for those T2 shine-through, it's bright, but here it's also bright in the ADC, and the lesion has low ADC value, so we can differentiate these two cases using ADC map. So when we will try to detect lesion, we will look both the DWI images and the ADC images. But when people talk about diffusion MRI, it can also be the diffusion tensor imaging. Physically speaking, diffusion tensor imaging, or DTI, is a matrix version of DWI. At each pixel, a tensor or a matrix is used that indicates both the magnitude and the direction of diffusion. So it incorporates the direction information. In this way, DWI can reflect the anisotropy of diffusion. It is very useful in the brain imaging because in brain, the water molecule, they diffuse, they preferentially diffuse along the axial direction. In today's talk, we first want to have a very brief review of the basic MRI physics because this is very helpful to understand DWI sequence. This is an MRI physics lecture, so we want to, one of our focus is the DWI sequence. We not only want to know how it looks, but we want to understand why it looks like that. And then we introduce the difference between ADC and DWI and how to use them to detect lesions. And we see some application of DWI ADC in both liver and in brain. Finally, we conclude with a very brief introduction about DTI. Review of MR physics. In the presence of a magnetic field B0, the tissue will demonstrate a magnetization M. When we apply a RF pulse or a B1 pulse, then the magnetization can be tipped down to the transverse plane. Then we stop the RF pulse, and the magnetization in the transverse plane will precess at a frequency omega. Omega equals gamma B0. This is Lamarck equation, very important. Ideally, if the magnetic field is B0, then the magnetization of all the small spins will precess at the same frequency omega. However, in reality, due to the micro-inhomogeneity of the magnetic field, not all the spins they experience B0. Some experience a little bit larger and some experience a little bit smaller. So B0 is a small range. And so they precess, the precessing frequency is a small range. Some precess a little bit faster and some precess a little bit slower. So after some time, then dephasing happens because they rotate at different rate. So their phases are different, and then this is called dephasing. So after dephasing, when we add up all the magnetization, the bulk magnetization is an exponential decay. Dephasing of spins will lead to decay of transverse magnetization, and transverse magnetization is the source of MR signal. So the MR signal will decay. This procedure we can illustrate it in the whole sequence diagram. This is 90-degree RF excitation, so we plot a 90-degree here, and then it decays. So the signal or the transverse magnetization decay, and different tissues have different decay rates. And this is a repetitive procedure. So after one excitation, they have another excitation. The time between two excitations is TR, and from excitation to the data acquisition, the time is called echo time or TE. By setting different value of TR and TE, different contrast can be obtained. Particularly if the TR is long and the TE is long, then we can get T2 weighting. Then this is the simple sequence. We can apply a 180-degree refocusing pulse after the excitation. This sequence is called spin echo sequence. The spin echo sequence, the purpose for this refocusing pulse is to eliminate the extra dephasing caused by the magnetic field inhomogeneity. And MRI gradient can be applied to the main magnetic field. Gradient basically just means the variation. So in the pulse sequence we plot like this, we mean we have a gradient. And what this means is due to the gradient, there will be variation in the magnetic field strength. So some have negative value and some have positive value. If we add up this change of magnetic field to the uniform main magnetic field, then the magnetic field will be a linear function. So forgetting all this detail, that means if we see in the diagram this type of thing, that means we have a gradient. And the result of this gradient is the magnetic field look like a linear function. It's no longer uniform. And the magnetic field gradient, we'll see very soon, it plays a very important role in the diffusion MRI. So briefly summarize the principle of MRI, which is very useful for our understanding of DWI sequence. The frequency depends on the magnetic field strength, and we can apply gradient. If we apply gradient, then the speed will be different, right? It's no longer uniform, it's a linear function. Then the frequency will not be the same, so it's omega prime. And different spin have different omega, and then the overall effect is the dephasing of those spins, and the dephasing can lead to signal decay. And the spin echo sequence means a 90-degree excitation and followed by a 180 refocusing pulse. The purpose is to eliminate the magnetic field inhomogeneity, and the T2 weighting can come from long PR and long PE. Okay, now we look at the diffusion weighted imaging. First, look at the sequence design. This is an excitation pulse, and this is the true acquisition. Between these two parts, we want to apply a gradient, magnetic field gradient. So like this, it can be positive or negative. So what this means? This means the magnetic field strength now is a linear function. So remember, omega equals gamma b. Here the b are different, so the omega is different. Some rotate because the magnetic field is low, is weak, so the frequency is small. They rotate slow, and with magnetic field strength grow stronger and stronger, this rotate faster and faster. So some rotate slow and some rotate fast, and those spins are defaced, right? And now we want to apply another gradient. This gradient, they have the same duration and same strength, but the direction is opposite. So here, notice that this is x, that means the location. For the same location, what question do you have?
No, I was just wondering if that had to do with when we do like MR body, like in phase, out of phase.
Yeah, it's different thing. I can explain that after class. So here, just now, we intentionally make this spin at this location to rotate slow. And now we do the opposite thing, have the opposite gradient, so it rotates faster. So at this time, it lagged behind others, but now it rotates faster and catch up. After this gradient, the refacing gradient, the spin, they rotate, and the rotation of the spin are refaced. So what we said is we can apply diffusion gradient, and after apply two gradients, one is defacing gradient and one is refacing gradient. Then the protons, they first get defaced, and then later on they get refaced. They can be fully refaced if they are static. However, due to the diffusion, that's the Brownian motion, those small protons, they don't stay there forever. So at this time they stay here, and later on they may stay here. And if the second time it's static, then they can reface. But if they move, then it's just partially refaced. It's not totally refaced. So this is called defacing. And as we say, as we review in the basic MRI, we know defacing can cause signal loss. This is just a demonstration of T2 defacing, but this is very similar, the similar result. So after apply a diffusion gradient, then due to the motion or due to the diffusion, then those spins are defaced, and the defacing will cause signal loss. It's an exponential signal loss. What we want to say is with gradient applied, the signal intensity is decreased relatively to those without gradient applied. And the decrease of the signal intensity is related with the extent of diffusion, how much you move. The farther you move, and the more decrease in signal intensity. So this is called diffusion-weighted imaging.
So we're measuring for the loss of signal and calling that signal?
Yes, we measure the signal and we can calculate the signal loss, and this loss is related with diffusion. Look at this. This is what we just introduced. Actually, the gradient or the diffusion gradient is not applied to those so simple sequence. It's most cases it's applied to a spin echo sequence. That means 90 degrees plus 180 degrees. The gradient is applied to the spin echo sequence. So compare with this. One gradient is applied before 180 and one is applied after 180. So the direction is flipped. Later on, in most papers, if you see the diffusion-weighted sequence, it just looks like this. But what this means, because it's before the 180 degree, actually the two gradients are the opposite direction. That's what we want to understand. And the reason we want to use spin echo sequence is to eliminate the magnetic field inhomogeneity. Magnetic field inhomogeneity can cause dephasing, but that's what we don't want to mix up with the dephasing caused by the diffusion. We just want to focus on the diffusion only comes from the diffusion, not from the magnetic field inhomogeneity. So we use spin echo sequence. And there are many types of spin echo sequence. We want to use a rapid acquisition. The reason is in rapid acquisition, images are acquired at a very short period of time, so patients don't have much motion, and the motion is reduced. And what we measure is just the Brownian motion or the diffusion. It's not the patient motion. And one of the rapid acquisition is EPI, echoplanar imaging. Diffusion-weighted sequence is always spin echoplanar imaging sequence.
Sorry, just to go back a little bit, when you said spin echo, the only thing that spin echo adds is that 180 refocusing pulse?
Yes.
And so the reason we do that is to eliminate the dephasing that's caused by the actual
magnetic field.
Magnetic field itself.
Yeah.
And so, okay. So how, sorry, maybe you were just about to get to it. So how are these different than?
Yeah. So here is spin echo, right? Here is spin echo EPI. Because spin echo, you can have fast spin echo. That's 90 degree plus 180 degree. Then later on, it just acquires several lines. The conventional spin echo just acquire one line at each TR. But if it's fast spin echo, you can acquire maybe several lines. But if you use EPI, then all the lines are acquired in one TR. So this is the fastest. Yeah, the last time we introduced the EPI, they try to acquire all the lines in one TR, and also they use this type of trajectory from left to right and right to left. But if you use fast spin echo, then always left to right. So that's just some details. The main idea is EPI is a very fast imaging sequence. So we use spin echo EPI for the diffusion weighted sequence.
Okay, so when we see diffusion weighted on a brain MR, it's most likely a spin echo, echoplanar
Yes.
sequence. With the diffusion gradient applied to that, or when I say spin echo echoplanar, does that imply the diffusion, or you have to say that as well?
We have to say that as well, because conventional spin echo EPI, they don't have this diffusion gradient.
Gotcha.
So this is the conventional one, and then here here I just want to say we want to add this part to the conventional one, and this is the conventional one. Now we can add the dephasing gradient to different direction, maybe to this slide selected direction, or the phase encoding direction, or the frequency encoding direction. And now notice that the TR is very long because there are so many points to sample. TR is very long, and also TE is very long because first we want to insert these two gradients. It takes extra time, and also the TR, you cannot start from excitation to this point. You also need to consider the effective TR. So maybe this point, so it takes very long to reach this TE. Sorry, it's long TE. So both long TE and the long TR, that means the sequence contains the T2 weighting component. So they have T2 weighting. Meanwhile, it has also the diffusion weighting.
When you said that we can apply it to the slice select, phase encoded, or frequency encoded, what does that mean exactly? We can apply the gradients to?
Because in the 3D space, we have X, Y, Z.
Oh, okay. So each one of those is X, Y.
Yeah, and so these are X, Y, Z, different direction, and so the gradient can be applied in either X or Y or Z, and so the measure the moving in that direction. Here, just briefly summarize what we just discussed. Diffusion gradient will be added to a spin echo sequence. The purpose of diffusion gradient is first to dephase and then rephase those spins. And due to the motion or due to the diffusion, proton cannot be fully rephased after this couple of gradients. So it's get rephased and so it's get dephased, and the dephasing can cause signal loss. This signal loss is related with how much you move, or the motion, or the diffusion. So this type of image is diffusion weighted imaging. And some details is why we use this spin echo EPI. Spin echo because we want to eliminate the external magnetic field inhomogeneity, which will cause the dephasing. And we want to use the EPI is because we want to reduce or minimize the patient motion and only measure the motion, Brownian motion that comes from diffusion. Diffusion weighted EPI sequence is a T2 weighted sequence because it has long TR and long TE. So it's both diffusion weighted sequence and the T2 weighted sequence. Now, we have introduced the diffusion weighted sequence, and we want to look at the signal intensity in the DWI image. We want to specify several parameters. This G means the strength of this gradient, and this small delta is the duration of this gradient, and this big delta is the time to diffuse, or the time between the dephasing and rephasing gradient. When these parameters are defined, we can define a B factor, which is a very important parameter in the DWI image. Some research show the signal intensity in the DWI is like this. It's S equals S0. This is the image acquired without diffusion gradient, and then exponential decay. So these formulas look complex, but intuitively we want to understand and perceive them. The diffusion weighted sequence, in there, the signal intensity is an exponential decay, right? And why it's an exponential decay? Just as we discussed, because diffusion or the Brownian motion, they cause dephasing, and the dephasing will cause an exponential decay. So the signal intensity in DWI is an exponential decay. That depends on those parameters. And we want to first look at this B parameter. What does that mean? And how it will affect the signal intensity. The B factor, this is just a constant geometric ratio. we ignore this. So B depends on G, delta, and delta. So if we have a stronger gradient or we have a longer gradient, then it will be a large B according to this equation. So what, the purpose of applying diffusion gradient is let signal to decay or dephase and decay. So if the gradient is stronger or the B is larger, then the signal decay will be greater. So a larger B will lead to a great decay in the signal intensity, like this. If we use a stronger or longer gradient.
We set the B. Oh no, B. We set the gradient. Is that which factors do we set?
The MR technicians just choose the B.
Oh.
Yeah, but what B mean? B actually mean if you choose this one, the machine will choose a stronger or longer gradient. And it's also possible if we expand the time to diffuse, then the B will be greater. So this means if we give them longer time to diffuse, then the B will be bigger. So that means here. In this way, we see with larger B or longer time to diffuse, then the signal intensity will decrease, but the contrast will be getting better. This is just like the T in the T2 weighted imaging. Smaller B or smaller TE, it will have a larger signal. A longer B or longer TE, then the contrast will be better. Just now we look at B, it's a operator control parameter. Now we look at the D, this big D. This is called diffusivity or diffusion coefficient, or later on we can call them ADC. That's the same thing. ADC or D, diffusivity or diffusion coefficient. That's basically an intrinsic characteristic of tissue. For the fluid, just as we said, fluid can diffuse very freely, so the diffusivity or ADC is great. And for solid tissue, they cannot move so freely, so the diffusivity is smaller than this one, than the fluid. And many lesions, the diffusivity will be restricted or decreased. So if we have a smaller D, according to this equation, the curve will look like this. Anytime we want to measure, then we see the diffusion restricted lesion, they will have stronger signal. And the stronger signal means brighter in the DWI images. So those lesions are brighter in DWI images and can be easily detected. Different tissues or different pathology, they have different signal intensity. That means the DWI images is diffusion weighted imaging. In DWI, we explained it contains both the diffusion weighting and also the T2 weighting. Remember, long PR and long PE. So that may have some problem. In what case the signal intensity in the DWI is bright? There are two cases. One is the lesion, which has the restricted diffusion that can look bright in the DWI image. And the other case is the diffusion is normal, however the T2 is long. In this case, because this S0 will be big, so it will also look bright in the DWI images. We want to eliminate the effect of T2 weighting, so we calculate the ADC. This is post-processed from the DWI image. This is the signal intensity comes from the DWI image with gradient, and this is without diffusion gradient. So we get these two images and do this processing. We get the D or ADC, apparent diffusion coefficient, or the diffusivity. Then we can get this value. Just repeat. For the fluid, the ADC value is very high, and the solid tissue it has relatively lower diffusivity than fluid. but those diffusion restricted lesion, the diffusion is restricted, so the ADC value is low. In the ADC, we eliminate the effect of T2 and only have the diffusion weighting. So if the lesion has restricted diffusion, then the signal will look dark.